In this video, we are going to look at an example of projectile motion and graph the velocity time graph and also look at the energy changes along the projectile path. All right, so let's read the question first. A golfer strikes a ball so that it leaves the horizontal ground with a velocity of 6 meters per second. So I guess this would be my U, and an angle of theta to the horizontal, as illustrated in figure 1.1. So there's a nice drawing here for you. There's a golf ball here that we will hit with a golf club and it will go pew, fly this way, sort of in projectile motion. Okay, so the magnitude of the vertical component, Vy, is 4.8 meters per second here. Okay, assume that air resistance is negligible. So in all your calculation-based question, air resistance will be assumed to be negligible for now. So A, show that the magnitude of the initial horizontal component, Vx, is 3.6 meters per second. Okay, so you may be thinking, teacher, I don't have theta. You know, I know this 6 meters per second. I split into 2, so I'll get this 4.8. But I am missing my theta. So if I'm missing my theta, I can't find Vx because, Vx is equal to 6 cos theta. Well, that's true. But also, don't forget that this can be recomposed. I can put it back into a right angle triangle. So I can redraw this diagram. So if I redraw this diagram this way, and this one here is 4.8, which means you move to the right, then you move upwards. So if you want to find Vx, it's pretty straightforward. You can equate to 6 cos theta, but even better if you use the Pythagorean theorem. So in this case, the hypotenuse 6.0 square, because the 90 degree is here, is equal to 4.8 square plus Vx squared. All right. So if you press your calculator, or at least you show this working, you should be able to get 6 minus 4.8 square. So answer, I got exactly 3.6. Yay! Meter per second. Okay, so this is 1 mark. Make sure you show this. Of course, if you want to, you can also use sine and cosine. So you can find the angle theta like this. For example, you could say 6 sine theta is 4.8. So from here, theta is equal to 53.1 degree. So I'll write this one here for you. 6 sine theta is 4.8. Theta is 53.1. So hence Vx is equal to 6 cos 53.1. And this will give me, should be the same answer or close to it, 3.60. So 3.6 meters per second. So it's up to you whether you want to find theta and then use 6 cos theta, or you can use Pythagoras. Okay, moving on to B. The part is asking you for vectors. So in B, it says the ball leaves the ground at t equal to 0 and reaches the maximum height at 0.49 seconds. Okay, on figure 1.2, which is the graph here, right beside here, this graph, sketch separate lines. So there are 2 different lines, okay, part 1, part 2, to show the variation with time t until the ball returns to the ground. For Vy, which is a vertical component of the velocity, and Vx, which is the horizontal component of the velocity. So in this case, right, you should know that if we are talking about projectile motion, let's say I draw the golf ball and the projectile like that. Okay, so I've said many times already, the horizontal velocity doesn't change. Why? Because there's no horizontal force. So this Vx is constant. And we already have Vx is 3.6. So constant and equal to 3.6. All right, so let me draw that part first. So this is my graph. 3.6. Let me zoom in. We'll take the right side as positive, okay? So this side here, because the question is insist in which direction. So I'm just going to use the line tool. Give me a sec to adjust. The 3.6 is roughly here. All right. So use your ruler and draw with me. This one is your VX. Label the line X. Okay, I label. All right. But teacher, I draw the graph from end to end. No, you must graph the motion. So at t equal to 0 here is where the golf ball leaves the ground. Here's where you leave the ground here. When is it maximum height? Let's check the question again. Okay, we're back here. So the maximum height is 0.49, meaning to say when you reach here is 0.49 second. And when you reach the lowest point here, behind my head, the lowest point here will be 0.49 times 2, which is 0.98. So the ball will only be in air until it hits the ground, because this is where you want to stop until the ball returns to the ground. So we need to stop drawing at 0.98. I know what you're thinking. You're thinking, teacher, this 0.98 is only one box there. Does it matter? Well, it does. It's stated in the mark scheme clearly that you should stop at 0.98. Okay, so make sure this part here, stop at 0.98, because you have enough information to sketch an accurate graph. Okay, what about Vy? Vy will go up and then come down, right? Because I guess I could draw the trajectory this way. It's going to go up and then come. At this point, at maximum height here, Vy is 0. So I'm going to label this point here as 0.49, right? So 49 is 49, 48, somewhere here, like half a box. So maybe I'll use green for this one, half a box. Okay. So here is where your Vy is 0. I think I will take, okay, again, for reference, I will use up as positive, and then I will use to the right as positive, like a normal person. Okay. So we will start off with the initial velocity when we launch here, remember? This one was 6, correct? And then we launch up here. This one is 4.8. Remember this? So we'll start with 4.8. 2, 4, 6, 8. Here is 8. Okay, so I'm going to join a straight line. Let's use green. Okay, I will join a straight line starting from here, 4.8, passing through 0.5. Okay, hang on, let me adjust my line a bit. So you draw together with me 0.8, sorry, 4.8, passing through this one. Teacher, where to stop? Then you stop at 0.98 lor. So use your ruler dengan beraninya, with all the courage that you can find in your heart, draw all the way until here. Okay, and if your line is perfect, it should start with 4.8 here. Okay, and then end at this coordinate here, this point, which is negative, sorry, not negative, y-axis first, which is 0.98, comma, negative 4.8. Okay, if your line is good lah. So this is your line Y. Okay, so graphing questions are very common. Here itself, you already got 4 marks, drawing 2 lines properly. So the horizontal component doesn't change, so it's going to stay at 3.6. So this part here is 3.6, right? So it's going to stay at 3.6 meter per second all the way. Okay, what will change is your vertical component. It will slow and stop. This is on the way up, positive. And then when it moves to negative, it will speed up in the negative direction, which is downwards. Go up, slow down, stop. And go down, speeding faster and faster, faster and faster, negative. All right. So if you're wondering where the marks are, I will show you the mark scheme now. So here's how you can get your 4 marks. 1 mark is when you start with 0, 4.8. Here. Okay. And you end at maximum height, reach 0 here. So they check the coordinates one, okay? The straight line will continue with the same slope to this ending point there here. So basically, if I see a straight line from 0.80 to 0.49, sorry, you will get 1 mark. So this and this with the line is 1 mark. Okay. Followed up by the same line continuing to this point is another mark. Of course, you have to label, right? Ladies and gentlemen, please make sure you label. Okay. For Vx, if you draw a horizontal line anywhere, you get 1 mark. And then it must pass through this point, start from here, and it must end here. Very important to end one box before 1.0, and you label this line X. So my friends, for graphing, right, if you have enough information, you should be able to show all the key values, the starting, where it reaches 0 at maximum height, the ending, and also stop at the right time, because this is when it hits the ground at 0.98 seconds. Is when you hit ground. Important time. Okay, so that's it. 4 marks for this graph. Okay, so even if you don't know how to calculate certain values, 4.8 is given to you. 3.6 is also given to you. You should be able to draw. Because they give you the value already, 4.8 is given in the question, 3.6 also given in the question. So if you know how to trend, this is just bonus. All right, let's move on to the next part. Part C. Calculate the maximum height reached by the ball. Well, I guess we have to STUVA now. So you could do STUVA. But when it comes to maximum height, I think the only thing I need is the Y component. Okay, so your S will be your H max, your H, maximum height H. T, we have 0.49. Thank you, question. U, we also have 4.8 meter per second. They're given in this question here. So not 4.8 Vy. Okay. V, final velocity is 0. So we will start here at 4.8, and then it will be smaller and smaller, and then become 0 up at the highest position. So this one is 0 at max height. Okay, what about acceleration? Well, my friends, acceleration is always the same downward g for Y component. So negative 9.81 or g. So I used, teacher, I can use any equation. Correct lah, you can use any equation because you got all the values. Just use the equation with S lah. So I think I will just copy an equation from the front. S is ut plus half at squared. Okay, so this one will be 4.8. You can use any equation that you want. Okay, plus half negative 9.81 t squared, 0.49 squared. If you're lazy, you want to pinda or move things around, then you just use the one with the S as the subject of your equation. Especially if you are, recording on a lazy public holiday. 1.17 meter. 1.17 meter. You can use any kinematics equation, or you can write 1.2. You can use any kinematics equation. Okay, can use v squared is u squared plus 2as. Can use s is half u plus v times t. Many options. Just make sure you remember that your u and your v is opposite, u and your a, sorry, is opposite sign. This one and this one opposite sign. Because one is pointing up, the other one is pointing down. So I write here for you. These two opposite sign. Because one is going up, then the other one is going down. Important, if not, you put different number here, you also wouldn't know. All right, so that's it for part C. Let's move on to part D. Part D, for the movement of the ball from the ground to its maximum height. Okay, once again, we're still moving, looking at the same ball. Ball is going to go to the maximum height here. Determine the ratio of KE at maximum height to GP, change in GPE. Okay. So I think the first thing that I should do is to remind you that if at this point in time in your studies, you don't know the equation or you don't remember the equation of KE and PE, well, then here is it. Kinetic energy at maximum height, you will take half mv squared, where v is the velocity at maximum height. Okay, so this v would be the velocity here. V. Okay, so v at max height. All right, and then you might be thinking, teacher, I don't have mass of the golf ball. Trust yourself. What you don't have, you don't need. Not now. So to find change in GPE, you will take mg, change in height. Okay. So I guess the m and m can cancel, teacher. Yeah, lor. So you don't need lah. Okay. So here you will have half. Hang on. What is the velocity or the speed at the highest point? Well, the highest point, Vy is 0, remember? So the only V that is remaining is Vx, which is your 3.6. So I will put 3.6 here. 3.6 square divided by 9.81. Change in height. Delta H would be the change in height from ground level to the maximum value. This delta H. Do we have to change in height? We did, remember? We look for the maximum height in part C. Come, I show you. No, the maximum height is here. 1.2, 1.17 up to U. Okay, so I'm going to put 1.2 lah. Okay, to follow the spirit of 2SF. So in that case, 0.5 times 3.6 squared divided by 9.81 divided by 1.2, that will give me 0.55. 0.55. So I'll put down the ratio here. And you might be thinking, teacher, so many marks 4 marks well, yeah, it's 4 marks. Let me zoom out to show you. But this is a easy AS question lah, okay? So if you write down MGH, you will get 1 mark. Not MGH. And if you write down half mv squared, you will get 1 mark. So 1 mark each for the equation. Okay. If you substitute the correct value, you get 1 mark, and then final answer is 1 mark. So meaning there are a lot of marks to be had, especially in certain questions. So always try a question. Don't leave it empty. Okay, next part. In practice, there's always air resistance, right? Explain why. So we want to know why the actual time taken for the ball to reach maximum height is less than the time calculated when air resistance is assumed to be negligible. So what they're asking for is, why does it take less time? Why less time to reach max height? Okay, so when you think about it, your max height is less. So you think about conservation of energy. So conservation of energy here, you see, if let's say there's air resistance. So right now, if you think about this, it will actually affect the maximum height because there's less kinetic energy to transfer to GPE. Okay, so if you're unclear, let me draw a diagram or let me do a separate calculation for you. We know the velocity here, this is 6 meters per second. By the time it reached the final position, it has decreased to 3.6. So if you want to, I can find the change in KE. The change in KE will be half m times 6 squared minus half m 3.6 squared. Okay, so here I'll have half m because again, I don't have m, but it doesn't matter. So this is 6 squared minus 3.6 squared. And this will be 23. Okay, which is also 4.8 squared. Teacher, sorcery. What sorcery? Remember, teacher, this upward movement is 4.8, correct? Okay, so you have this upward vertical motion. Okay, I draw for you. At this upward part, you have, okay, I need a bit of space. At this upward part, you have a velocity of 4.8, okay, meter per second, your Vy. So if Vy is 4.8 meter per second, by the time you reach here, this Vy will drop to 0. This is actually the Ke of the y component. So all of the Ke for the y component is actually converted to GPE. If you don't believe me, we can now do that ratio and see. Okay, give me a sec to clear the board. Okay, I made space, right? So right now, I'm going to show you a different way to find the ratio 0.55. Okay, so right now you can see that instead of taking the change in height, which I can easily get from part C, I can also take the Ke at max height, which is the Ke only due to the x component, divided by the Ke of the y component, because all the Ke of y component convert to GPE. So all of this converted to GPE. All right, let's put it in and see what we get. So this is half m 3.6 square divided by half m 4.8 square. So you can cut everything away and you'll get 3.6 over 4.8. When you square the whole thing, you'll get 0.56. Close enough. Okay, because this 1.2 we rounded, remember? We rounded from 1.17. So it's close enough. So here is the same answer. You can see, okay, 0.556, 0.55. So you may be wondering, why magic? No la. All the Ke that was lost, remember, this is the initial Ke, half m times 6 squared. Okay, I minus what is left behind. So I find the change in Ke. So this change in Ke, which is the decrease in Ke, is missing. It's the Ke that is missing. Okay, on one side, when I start, I have half m times 36. When I end, I have half m times 4.8, I mean 3.6 square. So 4.8 square is left behind. Okay, so right now, if you look at this, since all of this is converted to GPE. Okay, so in that case, if we want to consider the air resistance, how would air resistance affect this energy conversion? What happens when there's air resistance? So when there's air resistance, right, not all of this Ke will become GPE. Okay, so I'll write here in bracket. When there's air resistance, okay, so not all changes in Ke converts to GPE. And because of this, the max height decreases. And because of this, it takes a faster time, or time taken to reach max height is less. Time taken to reach is less. So you could do this, but there is another way to explain why the time taken is less. All right, so this one needs a little bit to borrow some ideas from dynamics or the next chapter, but I will draw it out for you. So let's say we have our good old ball that we have studied quite intensively in this question, and our ball will follow the trajectory. So I'm just going to draw the ball at different points in our trajectory, something like this. Okay, so my ball, golf ball, is going to decrease in velocity 0, vertical velocity, and then increase in the opposite direction. So if there's no air resistance, and if I draw this ball, if no air resistance, the only forces acting on the ball is weight. So you will have mg pulling the ball down. Okay, let's look at the first part of the motion, which is basically how much it takes to reach maximum height, this part. Okay, so mg is pulling downwards, but the ball is moving upwards. Vy is in this direction. The ball is moving up. Draw some smoke trail here. Oh, ball is moving up. Where is friction? Teacher, you friction oppose motion. Correct. So friction will fight the Vy. Friction will be like, yo bro, you want to go up? I'm pulling you down. So this is air resistance. Air resistance always will oppose V. Called resistance for a reason, right? So if mg and air resistance act in the same direction, can I say that now the net force on the ball, on our golf ball, in the downward direction, magnitude-wide increases? So because there is an increased net force in the downward direction, the second thing is your acceleration. Again, downward. Just going to put downward. Magnitude increases. So instead of 9.81, maybe you get 11. Maybe you get 12. I don't know. So this G, this downward direction A, is bigger than G, no longer equal to G anymore. Okay? So what will happen to the time of flight? You can always use your kinematics equation to judge. V is equal to U plus negative G or negative A T. Because A is in the downward direction, right? So when your V is 0, when this A, I can move things around. Oops, not sure what that is. When your V is 0, okay, I can move things around. Then what will happen now is I can write U is equal to AT. Because at max height, once again, V is 0. So I put this one at 0. So U is equal to AT. When U is equal to AT, if A increases, T decreases. So your explanation could be air resistance will change the acceleration of our golf ball. Okay, so you could say air resistance is opposite direction to V. Hence, larger resultant force. This question should be more than 1 mark. I think maybe they typo the marks. They shouldn't give the front part that many marks. Anyway, larger resultant force. So, greater downward acceleration. So, shorter time. All right, so that's the gist of it. In short, right, when it comes to air resistance, it's a little bit more thinking is required. It's not that complicated, but you need to think a little bit. Draw out the force diagram, like what I did for this ball here. Draw this force diagram. It will be quite helpful for you. Okay? And number 2, when you draw the force diagram, remember that at certain parts, the air resistance and mg will be in the same direction. Sometimes they'll be in opposite direction. If my ball is falling down, then it's a different story. But that one we leave for other questions. Okay? You think about it. What happens when the ball falls down? When the ball falls down, your air resistance will change direction. How will it affect the time of flight? You think about that. That would be somewhere in your homework somewhere, okay? In your past year questions, you need to try more questions, right? So in the short answer is when there's air resistance, the time of flight will be smaller because you don't reach that same maximum height. You reach less height, okay? So this purple one generally is not the best explanation, but it's the easiest to understand because we have done the calculation. Or rather, I've done the extra calculation. Extra calculation here being, we lose this much kinetic energy. We have lost this, oops, didn't change my pen. Why? We have lost this amount of kinetic energy. And because we have lost this amount of kinetic energy, we cannot gain back the same height if some of this kinetic energy is converted to friction instead of GPE. Okay, that was a 1 note lag. All right, so that's it. for this question. I think one last thing that I want to tell you is that because the mass m is cancelled, right? Your value of m is cancelled. So because it's cancelled, m doesn't affect max height. In fact, m doesn't affect anything in this diagram. Because the m and m cancel, doesn't affect max height. It will affect the magnitude, the absolute magnitude of the energy, but it doesn't affect the value of max height. Okay, because you can see my m and m cancel already. So if I replace the golf ball with a bowling ball, assuming I have enough energy to give the bowling ball the same initial speed, which is 6 meter per second at 53 degrees, then it's okay. So does it affect max height? As max height, if the initial conditions are the same. Okay, so if I can still kick the ball at 6 meters per second at 53 degrees, the ratios, the values, the maximum height, everything will still be the same. It's just that now if I want to kick a bowling ball or a football at 6 meters per second, I need to use a lot more energy. I need to use a lot more force, but the maximum height is the same. Okay, so that's it. Lots of all this extra detail that you need to think about. So I encourage you to try more questions, and I will see you in the next video or the next chapter. Bye-bye.